So, we have an optimization problem here. We have a rectangular storage container with an open top is to have a volume of 20 meters cubed. The length of its base is twice the width. The material for the base costs $20 per square meter. Material for the sides costs $10 per square meter. We want to find the cheapest such container. So first let's draw our box and assign variables to the parts that we don't know. So the length of the base is twice its width. So if I call this the width, then I might want to call this 2W. Alright. And then it's got a height, which we don't know. So right off the bat, if I want to write up the volume for this guy, I'm going to have length times width times height. So 2W squared times h. I'm just going to multiply those dimensions together. And we know that the volume has to be 20 meters cubed. There's our constraint equation. So now all we need is a cost function that we're going to minimize. Let's call it C. And so that's going to come off the price of the sides and the base. So let's put in a base here. The base is the expensive one. It costs $20 per square meter. So that means we need the area of the base. Well, the area of the base is 2W by W. So 2W squared is the area of the base times its cost, which is 20. Now we need to do the cost of the sides, which are only $10 per square meter. So let's take this side here. Well, it's 2W this way and H this way. So it's 2W times H. Well, so is this side that's opposite it. So we got two sides that are 2W times H, and they cost $10 per square meter. Now this side is W times H, and again there's two of them, one the front and the back. So we have the two that are W by H, and those are also $10 per square meter. Now it's kind of messy right now. We don't need this anymore. We got everything in our problem. But let's see if we can simplify. So we have the 2W squared, 2 times 20, which is 40, plus 2 times 2 is 4, times 10 is 40, so 40 WH plus 2 times 10, so plus another 20 WH. So those can actually be combined to make this a little bit easier to deal with. 40W squared plus 60 WH. Now we have a cost function, but it's in terms of two variables. So what we need to do is get rid of one of them. Probably the easier one to get rid of will be the H. So let's solve this guy for H so we can substitute out. H equals 20 over 2W squared, or just 10 over W squared. And I'm going to take that H and plug it in right there. So I have my cost function. I haven't done any calculus yet. We're just going to do a substitution here. 60W times 10 over W squared. And let's simplify so we can make this as easy on ourselves as possible. We can cancel out one of the W's with one of those, and we'll multiply the 6 by the 10. So 40W squared plus 600 over W. Or I'm going to write it this way: 40W squared plus 600 W to the minus 1, because we're going to be taking the derivative. So now that we have it simplified, we need to find any critical points. C prime. Alright, this is an easy one. Just a little power rule. It's 80W. This one's not too bad either. Minus 600. Bring the negative 1 down, so minus 600 W to the negative 2. Or we could rewrite this as 80W minus 600 over W squared. That's what we need to set equal to 0 for any critical points. So we get 80W equals, add the 600 over W squared to both sides, Okay, and now what I'm going to do is I'm going to cross multiply that W squared. So I have 80W cubed equals 600. Alright, and let's simplify this a little bit. Let's solve for W. Divide both sides by 80. We are going to get W cubed equals 7.5. And now what we'll do to get W is we'll raise both sides to the 1/3 power. So W equals 7.5 to the 1/3. And be sure when you put this in your calculator that you put the 1/3 in a set of parentheses if you decide to do it this way. So we're getting a W of about 1.957. Okay. Now, we do need to decide whether or not this is a min or a max, and I think it's going to be probably just as easy to use the second derivative test. So let's find C double prime. So the derivative of this guy, so that's 80. Bring the negative 2 down, so we got plus 1200 W to the negative 3. So if I plug in 1.95, that's going to be positive, which tells me it's concave up, which tells me I have a minimum because it's got to sit at the bottom. So this value for W does minimize my cost. Now to get the minimum cost, we could find H, but we're just looking for the cost, so all we need to do is plug that back in to our cost function, which we've found in terms of W. So we have 40 times, and we can actually, if we want, we can use the 7.5 to the 1/3 to make it a little more accurate, squared, plus 600 over 7.5 to the 1/3. So putting that all into our calculator, let's see what we're going to get. I'm going to actually kind of running this while we're talking. Give me just a sec. And you guys try along, just make sure we're getting this all in the same answer. I get to 2 decimals, since we're talking money, $459.79 is the cost of the cheapest such container.